All right, so let's take a look at our first section on vectors. Okay, again, it's section 8.5 in your book. If you're following along in the packet, it's 5.4. Again, all homework is going to be in the packet. All right, so first thing we'll start out with is the definition of a vector. Okay, a vector is used to model two things at the same time. Does anybody know what two things a vector models? Whether you draw the vector as an arrow, or you just write it with numbers.
Direction and magnitude?
Yep. It's a magnitude and a direction. Right. Somebody give me an example of something you would model with a vector.
Earthquake. With
With an earthquake, usually I think they just assign a number to it, like its magnitude, like a magnitude 5.2 earthquake, because the direction is kind of in every direction. So we're going to look at something a little simpler than that, something that's just in one direction, not traveling in all directions. Yep.
Velocity.
Yep, velocity. So whether you talk about throwing an object, a car traveling, plane traveling, okay, those are all examples of velocity. Okay. Anybody give me another category of things you might use a vector for? Besides speed as your magnitude?
Distance?
No, not thinking acceleration. What else can you model that it has a magnitude and it has a certain direction to it besides like a speed? I think I said it earlier. Talked about an object hanging from two cables. Force, right? So force, you have a direction you push, and you have how strong you push it. Okay, so that's a vector. Okay, and an example I can show you of velocity. If we take a look at, I have a website that shows different airplanes, right? So you could think of each one of these planes as a vector. Okay, if you click on one, each one of them has a speed and it has a direction. Okay, so let's just click on that one. Maybe. Right, and if we click it, we can see that its speed, in this case, is 278 knots, and its direction.
Direction is 422 SN.
422 SN. Right here? Oh, SM? Yeah, I'm not sure what that represents. That's distance. All right, so in this case, I'm not sure I can see the like the compass heading of the plane, but that's usually how they measure direction, okay, on a compass. Okay, but the idea is you can think of each one of these planes as a vector. A little more complicated because it's 3D. So each vector not only has a direction and a magnitude, but it has an altitude to it. So it might be okay that two planes are very close because one could be landing and one could be up at 30,000 feet. Okay, we don't know unless we click on them. Right? And it's the job of each kind of airport, each air traffic controller to figure out and coordinate all the traffic coming into their airport. All right. So if you start to zoom out, you can see thousands and thousands of flights. So it's a pretty complicated system to make sure we keep everything straight. But vectors are one way you could keep track of all these planes. All right. Okay. Any question on that example? Right, and again, we'll do an example with an airplane and like a jet stream, and we'll figure out what happens to the plane if the wind is blowing. Does it blow it off course? Does it speed it up? Does it slow it down? And it depends. It depends on which way the wind is blowing and which way the plane is going. Right, so one way you can represent a vector if you're thinking more of a visual approach is as an arrow. Okay, and an arrow works well because the length of the arrow can indicate the magnitude. And the direction that the arrow points, that's the direction of your vector. Okay, so as we start out, what we'll do is we'll draw vectors as arrows, and I'll show you how you can add them, okay, visually. And eventually we'll get away from doing it visually, and we'll just start doing it with numbers, just doing arithmetic. All right, but I think visual is important, especially when you get into word problems. Okay, because somehow when you get into word problems, you want to make diagrams. Usually your diagrams are going to have lots of right triangles in them, so sines and cosines come up. Right, so that's why we'll practice drawing some things visually. Right, so anytime you draw a vector, really it's marked by 2 points. Okay, I'm calling my points P and Q, where P is an initial point, Q is the terminal point. Now, if I switch the initial and the terminal point, would that make a difference? It would change the direction of it, but what wouldn't change? The magnitude. Yep. Okay, so if you switch P and Q, the direction changes, but the magnitude does not. And if I wanted to give a name to that, like in geometry, we might call this a ray, like ray PQ. In trig, we usually represent it as a single letter. You can either represent it as a letter with a line over it, or an arrow, or a bold letter. Okay, if you look in your packet, just on the first page, you'll see they use bold letters. Okay, I think when you're writing on paper, sometimes it's easier to just draw the arrow on top rather than the bold letter. It can be less confusing. Okay, so any questions on how you can symbolize a vector on paper? All right. All right, so the next thing we're going to look at is what happens when we add two vectors together. Okay, first thing to understand is when you add two vectors together, you get a new vector. Okay, when you add two vectors, you don't get a number. You get a vector. Right, and one way you can kind of think of that is if you had an object. Say you had a box on the ground, right? And let's say this point represents our box. Okay? And let's say you were pushing on the box in that direction, okay? And you had a friend also pushing on the box in that direction, okay, at the same time. What direction would the box move in? If one of you was pushing in one direction and then someone else was pushing the other way, which way would the box want to move? Yeah?
Diagonally opposite the combination, the meeting point of your two forces.
Yeah, so in this case, the box would want to move on a diagonal. Okay? You're pushing up, someone else is pushing left. The box is going to want to move up and to the left if you both push at the same time. All right? So that would be a new vector, a new magnitude, in a new direction. All right, so let's look at how we can add vectors graphically. Right, has anyone ever done that before? Adding them up? Okay, how do you do it? How did you learn in your other class? Yeah, Kenny?
Using coordinates.
Okay, so you can do it on a grid. How about if I just had a blank piece of paper and I don't really care too much about numbers. All I care about is the visual. If I have two vectors, I'm just going to visually add them, but I'm not going to measure anything about it.
Can I make a right triangle?
Okay, sometimes you can make a triangle. It depends if your vectors are perpendicular to each other, the forces. If they're not, we might not have a right triangle. Anybody else? Any thoughts on adding vectors visually? I haven't quite touched on what I'm thinking of here. So here's the idea. If you want to add, let's say you have this vector. You want to add it to that vector. Okay, I'll explain in words how you do it, but visually, you take one vector, take the other vector, and you position them so that the end of one lines up with the beginning of the other. So the terminal point of the one in black lines up with the initial point of the one in red. And then you draw from the initial point in black to the terminal point in red. That answer in blue is the sum of the red and the black. Okay, and it turns out it doesn't matter the order you do it in. Okay, if you added them that way, you're still connecting the terminal point of one to the initial point of the other, and you still get the same answer. All right. So visually, that's how you do it. And that's just describing it in words. Okay, position the vectors so that the ending point of V, okay, so in this case, this would be vector V, and the initial point of W, that would be in black. So they line up. Okay, next, draw in a vector from the initial point of V. Okay, so that would be from here to the terminal point of W. So right there. Okay, and that's the vector I just drew in blue. Okay, I don't know the direction of that vector. I don't really know the length. I didn't measure anything precisely. Again, at this point, we're just doing a visual process. That's all. So it's V plus W. And since I showed you earlier, V plus W and W plus V is the same thing, what property is that? Anybody think what property that is? It's commutative. Okay, so I'll mention that in a little bit, but vector addition is commutative. You can switch the order and get the same thing. Okay, questions on that? Okay, does everybody have the steps for adding visually? All right, so we'll try another example, just taking these two vectors and adding them up. Okay, if you do want some graph paper, I can print some out. I think my last class from Vectors last week, they used the end of it, but if you want some more, I'll print it and you can come back and get it later on. The stuff that I have, it prints like 8 grids, 4 on the front, 4 on the back, so you could do like 8 problems on 1 page of paper. All right, so let's add V plus W. Right. So if you don't have a grid, you don't even really need it. In fact, you can just do it right in your notes. I don't need the grid at all. So I'm going to take V, and I'm going to add W onto the end of it. That's the order they said to do it. V plus W. Okay, just finish up by drawing your answer. And what I just drew there is V plus W. And that's it. The answer is a picture. Okay, so on the test, what I might do with a problem like this, it could be a multiple choice question. Okay, I could give you 4 choices of answers. Maybe I'd have one vector pointing that way, have one pointing in the opposite direction, and then a couple other choices. And you'd have to figure out which choice is correct. Okay, or it could also be a true-false. I could say, does this plus this equal that? In this case, this is true. Okay? If I had it pointing the other way, that would be false. Okay. All right, let's try adding these up. Okay, before I do it, what do you think is going to happen here? Yeah, they cancel out. Okay, so remember, you have to connect the ending point of one to the beginning point of the other. Okay, so you start with that. Okay. Now, you would connect the initial point of V, which is right there, with the terminal point of W, which ends up being the same point.
Nothing. It's just a line.
So what would our answer be? Nope, it's not a point. Okay, we're close with 0. Remember, what do we always get when we add vectors? A vector. Okay, we can't get a number, but we can get what's called the 0 vector. Okay, the 0 vector is the only vector that does not have a direction, and it has no magnitude. What you can't write, or what would be wrong here, is if you put 0, the number. Because you don't add vectors and get a number. You add vectors and get a vector. Okay, so that problem really is just to illustrate this concept. This is called the 0 vector. And I think I mentioned this a little bit later on too. Okay. Questions on that one? Right, so when we're adding vectors, it is both commutative and associative. Okay, I already showed you commutative. I'll just show you one more time. Right, so commutative means I can switch the order that I add things up and I get the same answer. Right, so here's V, here's W, and this is V plus W. Okay, so I'll put that off to the side. Okay, now I'll switch it. I'll do W and then add V onto the end of that. All right, so let's take W. Oh, don't do that. Put V on the end, and now connect it again. Let's move that over here. And that one is W plus V. Okay, and I didn't use graph paper, so it might not line up perfect, but hopefully they're pretty close to the same thing. Yeah, looks pretty good. Right, so that shows you V plus W is the same as W plus V. How about associative? What does that mean if you just go back to thinking about like basic numbers? What's the associative property? Remember that? Brian, do you remember that? Associative? Well, it doesn't have to do with changing the order. We're gonna need 3 things, and we keep them in the same order on each side. But we're going to insert a symbol here.
Isn't the parentheses?
Parentheses. Right? So with associative, you're changing the grouping. Okay? You're changing the order of operations. Right? So this says that A plus B plus C equals vector A plus B plus C. And on the left, I'm adding A and B first. On the right, I'm adding B and C. Okay, let's do it. We'll do it both ways and see what happens. Okay, so the first way it says to do it on the left is to take A and B and add those up. Okay, so there's A plus B. It's almost horizontal, and Smartboard's having a hard time with dealing with that. All right, so that's A plus B. A plus B. And now on to the end of that, I'm going to add C. Okay, so take C, add that onto the end. And now I'm just going to connect, and I'm going to draw it by hand, where I start to where I stop. It's about like that. Right, so that's A plus B plus C doing it the way on the left. Okay, any questions on that? Right, now I'm going to do it the way it says to on the right. Okay, take B, add C onto the end of it, and do that first. Okay, this I should be able to draw because it's not close to horizontal or vertical. So that's B plus C. And now I'm going to take A and add that onto the end. So here's A. Add that onto the end. And we get that. So that's doing it the second way. And if I line these up, they are pretty close to the same thing. Okay, that's, again, kind of hard to write in your notes, but I'm just trying to show you visually that it's associative and commutative. All right, what's the difference between these two vectors? Okay, so visually, what does that mean?
Opposite directions.
Yeah, they point in opposite directions. What's the same about these vectors? The what? Sorry, I can't hear you. Derek, what's the same about them?
The same about them is they're both the same magnitude.
Yeah, they're the same magnitude. Right? So the difference is the direction they point. Specifically, they point in opposite directions. So later in the week, we'll get into finding the angle. If you have two vectors and you want to find the angle between them, we can do that. And for now, I'll leave that as a question we won't answer, but you can maybe think about what the angle would be between two vectors that point in opposite directions. Okay, what's wrong about that statement? I didn't intentionally write it wrong, I just noticed it is wrong. Shouldn't be 0. What should it be?
Yeah.
0 vector. Yeah. Okay, so you add two vectors that point in opposite directions. That's when you get the 0 vector. Now, we're going to kind of use this idea of pointing in an opposite direction to do subtraction. Okay, one way to explain subtraction, like when someone's really first learning about it, is you can put it in terms of addition. So if I said, all right, I don't want to explain to somebody how to do 2 minus 3. I want to teach them that as an addition problem. How would you write 2 minus 3 as an addition problem?
Negative 3 plus 2. Or 2 plus negative 3.
Yeah, we'll just keep it in the same order. 2 plus negative 3. Now, as long as they understand the concept of a negative number, I can say, now just do addition. Right? Well, we're going to do the same thing with vectors. Okay? We're going to subtract vectors visually. But instead of doing subtraction, we're going to add the opposite. Okay? That's how we're going to do it. We're going to add the opposite of the second vector. Okay? And what did we just say opposite means? It affects what? The direction. So all you have to do is, if you want to subtract, take your second vector, flip it around. Okay, it's like rotate it 180 degrees, and then add it. Okay, by flipping the direction, that makes it negative. And that's how we do subtraction. Find the opposite of the second vector and add. Right, so next one, they want me to do v minus w. Okay, before I even start, what do I have to find first? I need negative w. Yep. Right, and basically the way I can find negative w, if you remember from geometry, to make it point the opposite way, you just rotate 180. Or if you do a double reflection, it's the same as rotating 180. So I flip it horizontally, flip it vertically, and it's like I rotated it 180. All right, so now just take and think of this problem this way. Think of it as v plus negative w. So I've got v. I'm going to add negative w onto the end. Draw my vector. And that's it. That's my answer. That's v minus w. Okay, any question on doing subtraction visually? Okay, how about scalar multiplication? Have you talked about that in physics? What it means to scale a vector? If you haven't talked about it, I think it makes it's almost common sense. What do you think it means to scale a vector? What does it mean to scale something in general?
Change the size.
Yeah, to change the size, right? If I said I need a scale drawing of the house, right? Scale drawing means it's the same design, but it's just a smaller version. Okay? So what are the things that can happen when we scale a vector? The vector could become, and what do you mean by bigger? Magnitude-wise, and visually that would be represented longer. So longer arrow. What else? A shorter arrow. You could scale it larger, scale it smaller. There's one more thing that could happen. Everybody think about what's the third thing that could happen? Besides multiplying it by 0, because then that would make it the 0 vector. Multiply it by what?
A negative.
What would happen if you did that?
Then it would reverse the direction and also either make it longer or shorter.
Right, that could reverse the direction, and it could make it longer or shorter. Okay, so a scalar can really do three things. Make a vector longer, shorter, or flip the direction. Any question on that? All right, so notice in this kind of multiplication, we're not multiplying a vector times a vector. You can do that, okay? And there's two ways you can do it. We're not going to get that till that Wednesday on Thursday. Okay? For today, we're just going to multiply a number times a vector, not a vector times a vector. All right, so they've given us v. And I want to first find 2v. Okay, I have the bold v up above, but I think I'm just going to draw the v with the arrow so it's clear. Okay, how's 2v going to compare to v? Twice as long. And what's going to stay the same? The direction. Okay, scaling a vector does not change the direction unless you multiply by a negative. Okay. Right, so the simplest way to find 2v is just think of it as v plus v. Okay, add them together. And that's 2v. Okay, how about 1/2 v? Yeah, half as long. Okay, for that one, I don't really have a good way to do it, so I'm just going to estimate it. Half as long. Maybe about like that. 1/2 v. Okay, questions on those two? All right, how about negative 1v? Or you could just think of it as negative v. Yeah, just make it exactly the same length, but just rotate it. Okay, for me, it's easier to just flip it and flip it, but don't change the length. Okay, so there's negative v. What about negative 1/3 v?
Opposite direction. It's 1 times.
Yep. It's going to take v, it's going to flip the direction, make it a third as long. So I've already flipped the direction. Just take that and just try to estimate maybe where 1/3 is. Okay, so if you put 3 of those together, that would be negative 1/3 v. Okay, any question on that? Right, so those examples, all we did was practice scaling a vector with either a positive, negative, a number bigger than 1, or a number less than 1. Okay, now let's just look at what happens if we scale a vector and add. Okay, again, if you don't have a grid, you don't need it. Okay, because we're not measuring anything at all. Okay, so if I want to do 2v plus 3w. Okay, the hardest thing is if they do want you to measure something, you have to position the starting point somewhere where you're not going to go off the edge of the paper. Right? So if you look at v, you're going up and to the right. If you look at w, you're going down and to the right. So I would start way on the left-hand side, probably kind of in the middle. That should give me enough space that I don't go off the edge. Right, so I've got v plus another v. Okay, so that's 2v. And now on the end of that, just put 3 w's. Right, so there's 1, 2, and 3. Okay, and now what's my last step? Draw what? A vector, or an arrow, yeah. Right. So that's 2v plus 3w. Oops, I don't want that. Okay. Any question on how you do 2v minus w plus u? All you'd have to do is flip w around and then change it to addition. All right. Has anyone seen that symbol before? You take a vector and you put not just single bars around it, but double bars.
Absolute value of an absolute value.
It's a good guess. Have you seen that symbol in physics at all?
No.
No. So I guess some of the symbols we use are different. Okay. This symbol stands for the magnitude. Okay. So if they take a vector, put double bars around it, that means they want to know the magnitude. Okay, so since we're finding a magnitude, what do you know about this number? Something you... It doesn't what? True. Yep. It's just a magnitude. Okay. It's like measuring the length of the table. There's no direction. You just say the table's 8 feet long. It's not like it points in a certain direction. It's just that's the length of the table. So what else about magnitude? There's no direction. It's going to be a number. Can we be more specific than a number? Has to be positive. I guess if it was the 0 vector, it could be 0, so we have to say it's not negative. But it is always positive. Yep. Okay, how about the difference between the magnitude of v and the magnitude of negative v? Nothing. These are the same. Okay. What is different about the vectors, though?
Opposite direction.
They are pointing in the opposite direction, but once you take their magnitudes, we're disregarding the direction. Okay, if we talk about a vector that has a length of exactly 1, we call it a unit vector. Is that a term you mentioned in physics? No? Okay, unit vector is just a vector that's 1 unit long. Okay, remember when we did unit circle? That was a circle with a radius of 1. Unit vector, length of 1. Okay. For today, I'm not going to really do a lot with unit vector, but tomorrow we're going to come back to the idea of changing a vector into a unit vector. So don't change its direction, but I want you to either shorten or lengthen it so it's exactly 1 unit long. So it involves scaling it. And we'll do that part tomorrow. All right, so up until now, we've drawn vectors visually, which is fine. I think that's a good approach for a word problem. Try to draw your picture, see if you got some triangles in there. But if you really want to start doing operations on vectors and represent them in a way that's more efficient, okay, we need a new notation for vectors, something that's purely numeric rather than visual. And the first way we're going to do it is what's called an algebraic vector. Okay, an algebraic vector uses these symbols. Okay. Has anybody written a vector before with those angled brackets like that? Yeah, in geometry, that's how they do it. Another notation is IJ notation. We're not getting into that today. That'll be tomorrow. And does anybody know what is the A and what's the B here? All right, so kind of like X and Y. There's a real word here that you mentioned. They're the components. Yeah. Okay. The A is the horizontal component of the vector, and B is the vertical component. So in other words, if you start at an initial point, okay, and you can make your initial point anywhere you want, A tells you how far to move left or right from your initial point, and B tells you how far up and down to move from your initial point to get to the terminal point. Okay, so A is left and right, B is your up and down. Notice here, I wasn't very specific about the initial point. I just wrote from an initial point. So what does that mean? It means you could put your initial point anywhere you want. If I said to sketch a vector and I gave you 2 numbers. Okay? This notation doesn't really tell you where to start. Right, so I'm going to graph the vector 2, 3. But again, it just says from an initial point. Doesn't tell me where in the plane I should really start from. Yeah, you could start from the origin. You can start anywhere you want. If you start from the origin, that has a special name, which I'll mention in a second. Right? But if I start here, A tells me to go 2 units right. B tells me 3 units up. Okay, so there's the vector 2, 3. I could start here and go 2 units right and 3 units up. Let's fix that one. So 2, 1, 2, 3. Okay, we can put it anywhere you want, but A gave the suggestion of starting from where? Yeah, why don't we start from the origin and go 2 units right, 3 units up. Okay, I'm just going to put 1 more in quadrant 1. You'll see why in a second. 2 right, 3 up. Okay, so if you do start your vector at the origin, okay, that's called a position vector. And it makes it easier to work with because the initial point is 0, 0. Okay, just arithmetic-wise, things work out easier. All right, what I'm going to do is I'm going to look at one of these vectors, okay, and I'm going to try to figure out what its position vector would be. We know it should be 2, 3. But I'm just going to give you the initial and the terminal points and see if you can figure it out from the coordinates. How would we get a 2 and a 3? All right, so let me make it a little bigger. Okay, let's make it bigger. Let's just focus on the one in quadrant 1. Okay. Anyone tell me what the initial point what the coordinates are?
5,
1, 2, 3, 4, 5, 2. Yep. And how about the terminal point?
7, 5.
Yeah, it looks like 1, 2, 3, 4, 5, 6, 7.
5.
All right. So if you were just given, this is your initial point. This is your terminal. Does anybody see what you would do with those coordinates to get? Yeah, you just subtract them. Okay. If you take 7 minus 5 and 5 minus 2, 7 minus 5 gives me 2. And 5 take away 2, there's my 3. Now, what order did I subtract them in?
Terminal
Terminal minus initial.
Right, you've got to do terminal minus initial. So what we'll do to set that up is we'll call it like x1 and x2 and y1 and y2. Right, so suppose you have a vector that has an initial point. I'm going to call the initial point P1, and those are its coordinates. The terminal point is P2, and those are its coordinates. Okay, very easy to find the position vector. Terminal value minus initial for the x's. Terminal value minus initial for the y's. What would happen if you subtract in the wrong order? You would get the negative of your vector, which would mean
the opposite way it's supposed to.
it's pointing the opposite way. It would be the correct magnitude if you measured it, but it would be pointing the wrong direction. It's very important you follow this formula just the way it is. Okay, does everybody have the formula for finding a position vector?
Not yet.
Okay, I can leave that up. All right, so here they've given us 2 points. Okay, even if they don't tell us which one is initial and terminal, always assume the P1, that's your initial, P2, that's terminal. All right, so what am I going to write? You don't have to give me the final answer. I just want to know what minus what for the horizontal component. 4 minus negative 1. And for the vertical? 6 minus 2. Okay. This one was important because if you forget the extra negative, it's going to mess things up. So 4 minus negative 1. 5. 4. Right, so what that means is if you wanted to draw this vector starting at the origin, 5, 4 would be your terminal point. Go 5 units right, 4 units up. Now, would it be okay instead of using angle brackets if I used parentheses?
No.
No. Why? What would that be?
A point.
Yeah, now if you do that, you're writing a coordinate. Okay. What if I just use regular brackets? Is that okay? No. Brackets are usually when you have a list of numbers, you put them in brackets. Okay. This is the list of numbers 5 and 4. Okay, this is a list. We don't want that. We don't want a coordinate. We want a vector. Okay, so make sure you use the angle brackets. Okay, tomorrow we'll come up with a way of writing this without brackets. Has anybody written stuff like this in physics? 5i plus 4j? No? All right. We'll talk about this tomorrow. Okay. All right. So the homework, again, it's in your packet. Okay. Do not use your book. Okay. You don't even need to bring your book for this week. Okay. In the packet on page 344. Okay. Try 1 through 10 all. 14 to 22 even, and 26 to 32 even. But just find the position vector. Okay, they're asking you to do something with i's and j's. If you've done that, you could do it. But if you haven't, just find the position vector on 26 to 32. All right, so you got about 15 minutes. Okay, so please use the time to try to get started. Okay, if you have any questions, let me know. If you finish it, just show me it, and then there's no homework. But probably won't take much more than 15 minutes.